All right, so today we will finish Unit 6 on chi-squared. And we did chi-squared goodness of fit test where we had a single sample, that was a categorical variable, but more than two categories. So we couldn't fit it into a one prop z test or a two prop z test. Right? Today we're going to look at two other procedures for chi-squared. And these ones are inference for two-way tables. We've already looked at two-way tables back in topic 5 when we looked at segmented bar charts and independence through that. Today we're going to do a chi-squared test of homogeneity and a chi-squared test of independence. So a chi-squared test of homogeneity tests to see if all category proportions are the same for all populations compared. So our test of homogeneity, we're going to have multiple samples. Right? So we're going to have more than just one sample. That's one way to check. So we could have 3 different random samples and several categories in each of those samples and compare, see if the proportions are the same across those different samples. And then a chi-squared test of independence has to see if the row variable and column variable are associated or not. Right? So this one, homogeneity, multiple samples, right? One variable measured. And this is a single sample with 2 variables measured. So for each observational unit, we're going to record 2 things. All right, moving forward. How to determine a test of independence versus a test of homogeneity? You don't necessarily need to write this down. Let's just take a look at this. So suppose we are examining how socioeconomic status is related to smoking. If we sample 600 adults and categorize them with respect to their socioeconomic status and whether or not they are smokers, we're examining independence. We have a single sample and 2 variables. We take each person, decide whether they smoke or not, and then just describe them as low, middle, or high socioeconomic status. On the other hand, if we drew a random sample of 200 low, 200 middle, and 200 high socioeconomic status and found out whether they are smokers or not, you're doing a test of homogeneity. We have multiple samples and a single variable measure. As opposed to the goodness of fit test, right, where we had a single sample, right, with 1 variable, right? So we had a single sample, 1 variable with more than 2 categories. That was our chi-squared goodness of fit test. So the chi-squared test of homogeneity and the chi-squared test of independence function exactly the same. Okay? If you have a row by column matrix, the degrees of freedom are calculated by taking row minus 1 times column minus 1. So these are things you definitely want to jot down. The expected count for a two-way table is the following. So let me go ahead and give you a quick example here. So let's say I have a very small matrix. And let's say we have 17. All right. And we have our totals here. 27, 32, 21, 40, 40. And our table total right there is 80. So I'm going to create a new table with expected counts. So let me show you how this is calculated using just one. And since these get a little bit large, especially when we need to have expected counts for maybe even a 3x3 or 3x4 table, we're going to rely on our calculator for the most part. But here's how the expected count for each one is calculated. So E is going to be the row total. So let's say E 1, 1, right? So this expected count for this particular value in the table. We're going to take the row total. So the row total right here, 40, times the column total right here, divided by the table total, that 80 right there. So each cell within our matrix is going to have its own expected count. Remember what we're doing with all the chi-squared? We're comparing observed to expected count. So the expected count right here would be 13.5. Okay? Then we go across and do that for each of them. Typically, if you're asked, say, on a multiple choice question, you'd only have to calculate one or two. Okay? So the conditions are also identical to the chi-squared goodness of fit test. No more than 20% of the expected counts can be less than 5. Typically, we're going to see this that all expected counts are greater than or equal to 5. Okay? And simple random sample, of course. And the test statistic and p-value calculated using matrices. We could do it by hand, but consider this. We'd have 6 different contributions to our chi-squared test statistic. So the calculator will help us out a lot. All right? We're going to use the matrix function in our calculator. I'll let you guys give you a chance to catch up on that. So remember when we're doing this, our chi-squared test statistic is just the same, right? The sum of all the observed minus expected squared over expected. So each value within our two-way table has an observed, that's 17 there, and then the expected, the 13.5. So we can calculate that contribution, for example, right? The contribution for that first part would be 17 minus 13.5 squared divided by 13.5, right? Because that's the expected count that we calculated there. So each of those particular cells within our matrix, we would go ahead and count the contribution. And at the end, we add them all up to our chi-squared, and then we can calculate our p-value. Right. So let's go through a couple of examples. All right, so this is an example of a chi-squared test of homogeneity. So taxicabs were randomly selected in 3 different eastern cities. We want to test the claim that the 3 cities have the same proportion of taxicabs with functioning seatbelts. All right. So here's how our null and alternative hypothesis work for all of these tests. Right? Make sure we do a complete test, identify the correct procedure. We're going to say a chi-squared test of homogeneity. Here's our null and alternative hypothesis. The cities have the same proportions of taxis with seatbelts, and the proportions of taxis with seatbelts are not the same. Or at least one differs. Okay? You can always say that at least one differs. We're not given a significance level. I'm going to choose 0.05. Let's go ahead and verify our conditions. Our conditions. 1, SRS. That's stated in the problem. Can we see that? Right there. It says randomly selected. We're happy with that. Now we need to go ahead and calculate our expected counts. So we're going to use our calculator for that. All right, so now that we have our expected counts, we're going to write those right in the table here. And we use the matrix function in our calculator to go ahead and run this test and find those expected counts. And notice we're not given any contributions here, so typically we don't look much further than just comparing the observed and the expected. Are all of our expected counts bigger than 5? Yes. So we can write that as our second condition here. All expected counts are greater than or equal to 5. See table above. And then we ran our chi-squared test. Then we had a chi-squared of 42. And our p-value, approximately 0. Now let's report our degrees of freedom. What were our degrees of freedom? 2, right? Degrees of freedom were 2, right? We have number of columns is 3. So 3 minus 1. Number of rows, 2. 2 minus 1. So 2 times 1, there's our degrees of freedom. That's how those are calculated. So your calculator will spit that out for you. They're fairly straightforward. So since 0 is less than 0.05, we're going to reject our null hypothesis. So we're going to say at the 5% significance level, there is sufficient evidence to say, then we can just go up and restate our alternative hypothesis. The proportion of taxis with seat belts are not the same in the 3 cities. They're not the same in New York, Chicago, and Pittsburgh. Recording. All right. So our last test is our chi-squared test of independence. So this is where we have a single sample. We have 2 variables measured, and I want to see if the two variables are related. Is there an association between the two variables? So this question, do angry people have more heart disease? A random sample of 8,474 people from 3 locations were studied for 4 years. All subjects were free of heart disease at the start. Subjects were given the Spielberg Trait Anger Scale test to measure how prone they were to sudden anger. 3 levels of anger were determined: low, moderate, and high. Subjects were classified as having coronary heart disease if they had a heart attack or needed medical treatment for heart disease. All right, so let's look at our two-way table and see what we have here. So we have our low, moderate, and high. We have our table totals, and we have heart disease or no heart disease. So these tests, quite simple. Let's just go through these. This is a chi-squared test of independence. And our null and alternative hypothesis anger level and coronary heart disease are independent. The null hypothesis is always this. You can say are independent, are not related, and anger level and coronary heart disease are not independent. I want to go as far as say it's dependent, but not related or related. That would be a better way to say it. And we're not given a significance level, so I'm going to choose a, let's write a 5%. And just check our conditions. SRS stated in the problem. And then we need to verify our expected counts. So I'm going to give you a second to go ahead and type this matrix into your calculator, and then go ahead and run the test and find the expected count. See if you can come up with the chi-squared value, your p-value, and your expected counts. So word to the wise, when we're entering the matrix, we do not put the totals in there. So don't put the totals in there. All right, so from my calculator, again, I'm going to gather the expected counts from matrix B and put them right in my table here. So and since I'm just using these to verify these, notice in our calculations we wouldn't necessarily round these, but to check conditions, it's okay to round. So my expected count in the table. All expected counts are greater than or equal to 5. See table. And my chi-squared at 16.08. My p-value 0.00032. My degrees of freedom, again, were 2. We had 3 columns. 3 minus 1 is 2. 2 rows. 2 minus 1 is 1. Yeah. 2 times 1 is 2. And that small p-value is going to lead me to reject my null hypothesis. So remember, small values of p, our p-value, give us strong evidence against our null hypothesis. So at the 5% significance level, there is sufficient evidence to say there is a relationship between anger levels in coronary heart disease. All right. So here's spelled out very clearly all the steps to our chi-squared test of independence. Step 1, state our hypotheses. Anger and coronary heart disease are independent. Anger and coronary heart disease are not independent. Is it a random sample? Stated the problems were good. And then we ran the matrices and checked the expected values. They were all greater than 5. Calculated our chi-squared test statistic. Right? We entered our cell counts in the matrix A on the calculator and ran the chi-squared test. The expected counts would be in matrix B. We're going to write them next to the table. And then our conclusion in context. We had a small p-value. So in this case, we have strong evidence that anger and heart disease are not independent. In other words, they appear to be related.